What secrets lie in the vastness of the universe? How did the cosmos come to exhibit such astonishing uniformity across incomprehensible distances? Could our understanding of the universe's origins be incomplete, or are we simply witnessing an extraordinary cosmic coincidence? High above the swirling atmosphere of a distant planet, a telescope orbits silently. Its curved mirror collects ancient light, a faint echo of the universe's past. The instrument adjusts, turning its gaze from the bright stars of its local system to the darker, more enigmatic corners of the night sky. Beneath it, the alien world rotates, its white clouds twisting gently under the light of an alien sun. From its vantage point above the atmosphere, this telescope enjoys a clarity of vision unmatched by any ground-based observer, revealing the grand structure of the cosmos. The closest stars, mere light years away, appear as solitary points in the blackness, each a unique sun akin to the one hidden behind the planet below. But beyond these nearby stars lies a sprawling galactic plane, a dense, radiant band that stretches across the sky. This plane marks the center of the galaxy, an immense spiral of stars and interstellar matter stretching over 100,000 light-years and containing some 400 billion suns. Yet the telescope's focus shifts again, peering above the galactic plane where the stars thin out. Here, dim, multicolored smudges paint the sky. Each smear is a galaxy, a collection of billions of stars, their light diminished by the immense distances separating them from the observer. The telescope maps these galaxies with precision, revealing that they are not evenly distributed but instead cluster together in a local group. Beyond this, the instrument detects fainter structures, clusters of galaxies, and even larger superclusters stretching hundreds of millions of light-years, separated by vast, empty voids where no light or matter can be found. At the very limits of its reach, the telescope glimpses the edge of the observable universe. This faint horizon, some 45 billion light-years away, marks the boundary beyond which light has yet to travel to us since the beginning of time. Through this single lens, the structure of the universe is laid bare, an intricate web of galaxies, clusters, and voids, extending outward in all directions. But this telescope is no earthly creation. It orbits a planet far removed from our solar system, circling a foreign sun within a galaxy that is not the Milky Way. Our home, the Earth, lies somewhere beyond its gaze, hidden within the vastness of the cosmos. Yet remarkably, this alien perspective offers a universe that looks strikingly familiar. No matter where you stand in the cosmos, the large-scale structure of the universe remains consistent. The temperature of the cosmic microwave background is uniform. The lumpy distribution of galaxies, clusters, and voids persists. The universe appears isotropic and homogeneous, as if sculpted by some invisible hand to be the same everywhere. This raises a profound question: how can parts of the universe so distant from each other, separated by tens of billions of light-years, be so similar? These regions could never have exchanged information or energy, as light itself has not had enough time to traverse the gulf between them since the beginning of the universe. This horizon problem has challenged cosmologists for decades, pointing to a gaping hole in our understanding of the universe's origins. To unravel this mystery, scientists must journey back to the very beginning of time, to the origins of the universe itself. The prevailing theory, the Big Bang, suggests that the universe exploded into existence 13.8 billion years ago, expanding rapidly from an unimaginably small and dense state. But this explanation alone cannot account for the observed uniformity. Instead, we must delve into the realm of quantum mechanics, where the tiniest fluctuations in the fabric of reality could have been stretched across the universe during an epoch of rapid inflation, a fleeting moment when space expanded exponentially faster than the speed of light. This inflationary model, while elegant, raises new questions. Could our universe be but one bubble in a vast multiverse, each bubble with its own physical laws and conditions? If so, how do we reconcile the apparent uniformity of our cosmos with the chaotic diversity that such a multiverse implies? To answer these questions, we must confront the deepest mysteries of physics. What mechanism drove inflation? Was there truly a bang in the Big Bang, or is this term a simplification for a process far more intricate? Is the observable universe merely a fragment of a grander, more complex reality? Around 13.8 billion years ago, the universe began, or so our best evidence suggests. Yet, despite the clarity of the observations and the elegance of the mathematics, we do not fully understand how it happened. What was the universe like in its very first moments? What forces governed its behavior when it was unimaginably small and incomprehensibly hot? Our theories, based on centuries of observation and logic, offer a compelling narrative, but cracks in this story raise questions that cannot yet be answered. In the 1920s, Georges Lemaitre, a physicist and Catholic priest, proposed that we live in an expanding universe. His calculations, bolstered by Edwin Hubble's later observations of redshifted galaxies, revealed that distant galaxies are moving away from us, their light stretched into longer, redder wavelengths as space itself expands. The further away a galaxy lies, the faster it appears to recede, a phenomenon that could only arise in a universe that has been growing since its beginning. This revelation gave birth to the Big Bang theory, a universe that started small and hot before expanding into the cosmos we observe today. But even as this theory rose to prominence, cracks in its foundation began to emerge. Several perplexing features of the modern universe seem to defy the predictions of a simple, steadily expanding cosmos. These anomalies, known as the horizon problem, the flatness problem, and the absence of magnetic monopoles, present challenges that could undermine the very core of the Big Bang narrative. Imagine standing at one end of an infinite desert and seeing an oasis at the horizon. Now imagine someone at the opposite end of this desert, billions of miles away, observing the same oasis. How could the two ends of such a vast landscape share the same feature? The horizon problem is much like this. No matter where we look in the universe, the cosmic microwave background radiation, the faint afterglow of the Big Bang, appears remarkably uniform in temperature. This radiation suffuses the universe, raising the temperature of space to just a few degrees above absolute zero. For this homogeneity to exist, all regions of the universe must have been in thermal contact long enough to equilibrate, just as a room eventually evens out in temperature when heat is distributed. But here lies the paradox. In an expanding universe, regions separated by billions of light-years are beyond each other's causal horizons. They could never have been in contact to exchange energy or information, even in the earliest moments of cosmic history. How, then, did these distant regions come to share the same temperature? This puzzle suggests an extraordinary degree of fine-tuning in the universe's initial conditions, a statistical improbability that defies the laws of physics and probability. Einstein's theory of general relativity describes spacetime as a malleable fabric, warped by the presence of matter and energy. The shape of this cosmic fabric depends on the universe's overall density. If the density is too high, the universe curves into a spherical shape, eventually collapsing under its own gravity. If the density is too low, the universe takes on a hyperbolic, open shape, expanding forever at an accelerating rate. Between these two extremes lies a delicate balance, a flat universe, with just the right density for expansion to slow infinitely over time without collapsing. The odds of the universe naturally achieving this balance are infinitesimally small, akin to flipping a coin and having it land perfectly on its edge. Yet, when astronomers measure the curvature of space, they find it to be astonishingly flat, to an almost unimaginable precision. How could the universe begin with such an improbable density, poised perfectly on this cosmic knife edge? This apparent fine-tuning suggests either an extraordinary coincidence or that our understanding of the early universe is incomplete. In theory, the early universe should have produced a plethora of magnetic monopoles, hypothetical particles that carry a single magnetic charge either north or south, unlike the dipole magnets we are familiar with. These monopoles are predicted by grand unified theories of particle physics and should have been created in abundance during the intense heat of the universe's earliest moments. Yet, despite extensive searches across all scales, no monopoles have ever been found. Their absence poses a direct challenge to our models of the universe's earliest epochs. These three challenges, horizon, flatness, and monopole problems, have forced cosmologists to reconsider the simplicity of the Big Bang model. Could the early universe have undergone a period of rapid inflation, stretching space exponentially in the tiniest fraction of a second? Inflation theory, proposed in the 1980s, offers a tantalizing solution. By expanding the universe faster than the speed of light, inflation could homogenize temperatures across vast distances, flatten spacetime, and dilute any primordial monopoles to undetectable levels. But even inflation raises deeper questions. What caused it to begin, and what caused it to end? Could our universe be part of a larger multiverse, with different regions experiencing their own unique inflations? Are the initial conditions of the universe determined by quantum fluctuations on a scale we cannot yet comprehend? The story of the Big Bang remains a work in progress. It has provided a framework to understand our universe's past and future, but its mysteries remind us of how much we have yet to learn. As we peer deeper into the cosmos and refine our theories, the answers we seek may reveal not only the origins of our universe but also the very nature of reality itself. Alan Guth and the Revolution of Cosmic Inflation. What lies at the very foundation of the cosmos? How did the universe transition from a chaotic, infinitesimal beginning to the structured vastness we see today? These questions, as compelling as they are elusive, occupied the thoughts of Alan Guth on a fateful evening in Menlo Park, California. Late into the night, amidst pages covered in equations and musings, Guth reached a realization that would forever change our understanding of the universe: cosmic inflation. By the late 1970s, Guth was an ambitious physicist facing a fiercely competitive academic world. He had immersed himself in the mysteries of particle physics and the early universe, particularly the conundrum of missing monopoles, hypothetical magnetic particles predicted by grand unified theories. Despite his determination, Guth felt the weight of an unsolved puzzle. Why did the universe appear so uniform and vast, yet seemingly inconsistent with the predictions of the standard Big Bang theory? That evening, inspiration struck. Guth proposed that the universe, in its earliest moments, underwent an extraordinary phase of exponential expansion, a period of cosmic inflation. This profound insight not only addressed lingering questions about the Big Bang but also provided a coherent framework for understanding the large-scale structure of the cosmos. Though the Big Bang model elegantly explained phenomena such as the cosmic microwave background radiation, CMB, and the relative abundances of light elements, it left critical gaps in our understanding of the universe. The CMB, the faint afterglow of the Big Bang, exhibits an almost perfect uniformity in temperature across the sky. However, in a universe expanding at a constant rate, regions separated by vast distances should never have been able to exchange energy or information. How, then, could they have reached such thermal equilibrium? Einstein's general relativity suggests that the geometry of the universe depends on its density. A slight deviation from the critical density would lead to a universe that either collapses in on itself or expands uncontrollably. Yet observations reveal a universe that is astonishingly flat, defying expectations without extraordinarily fine-tuned initial conditions. Grand unified theories predict the formation of magnetic monopoles in the early universe. These particles, if they existed, should be abundant. However, despite extensive searches, no monopoles have ever been observed. This glaring absence remained a major challenge for cosmologists. Guth's theory of inflation proposed that the universe underwent a period of rapid exponential expansion within the first tiny fraction of a second after the Big Bang. This dramatic growth smoothed out irregularities, resolved inconsistencies, and created the conditions for the cosmos we observe today. Inflation was driven by a scalar field, a theoretical energy field that permeated the early universe. This field became temporarily trapped in a high-energy state, driving rapid expansion. When the field transitioned to a lower energy state, it released immense energy, reheating the universe and producing the particles and forces we observe today. The implications were staggering. In a mere 10 superscript 3 seconds, the universe expanded by a factor of 10 superscript 3. A region smaller than a proton balloon to a size comparable to a grapefruit. This exponential growth provided a natural explanation for the universe's vastness and uniformity. Before inflation, the entire observable universe was a tiny, connected region where thermal equilibrium could be established. Inflation then stretched this region exponentially, explaining why the CMB appears so uniform across vast distances. Inflation flattened any initial curvature in the fabric of spacetime, much like inflating a balloon smooths its surface. This process naturally explains why the universe appears so flat, without requiring improbable fine-tuning. In the early universe, monopoles may have been created in abundance. However, inflation diluted their density by stretching space, rendering them so sparse that none are detectable within the observable universe. While Goose's initial model was groundbreaking, it required refinements to align with observations. Physicists such as André Linde and Paul Steinhardt introduced new models of inflation, including chaotic inflation and new inflation, which provided more robust mechanisms for the onset and conclusion of inflation. One of the most provocative implications of inflation is the possibility of a multiverse. In some models, inflation never completely ends but continues indefinitely in isolated regions, creating bubble universes with distinct physical properties. Our universe would then be one of countless others, each with its unique characteristics. Inflation makes several testable predictions, which have been supported by observations. Primordial gravitational waves, ripples in spacetime generated during inflation, leave subtle imprints on the polarization of the CMB. While definitive detection remains elusive, experiments such as BICEP-2 and future observatories aim to uncover this evidence. Quantum fluctuations during inflation were stretched to macroscopic scales, seeding the formation of galaxies and clusters. Observations of the cosmic web align remarkably well with these predictions. Alan Goose's theory of cosmic inflation revolutionized our understanding of the universe's origins. It provided a coherent solution to long-standing problems, connecting the smallest quantum phenomena to the grandest cosmic structures. Yet, as with any transformative idea, it raised new questions. What triggered inflation? What caused it to end? What lies beyond the observable universe? As experiments probe deeper into the cosmos and theories evolve, we move closer to answering these profound questions. Goose's work stands as a testament to the power of human curiosity and imagination, reminding us that the quest to understand the universe is as infinite as the cosmos itself. Outside, the temperature has plunged below -50 degrees Celsius, and the howling winds batter the curved walls of the station. The starlight alone illuminates the icy expanse, a stark and unyielding landscape. Yet, within the heavily insulated control room, a faint mechanical hum from a giant microwave telescope signals the relentless pursuit of understanding. Perched at nearly 3,000 meters above sea level on the high Antarctic plateau, the telescope scans the cosmos with unparalleled clarity, its mission to detect the faint imprints of inflation embed. Inflation, for all its elegance and problem-solving prowess, remains an unproven hypothesis. Its mathematical beauty has captured the imagination of the scientific community, providing a unifying framework that bridges particle physics and cosmology. Yet the ultimate proof of its occurrence lies in the details /U 2014 in the elusive remnants of that moment of extraordinary expansion. To understand the stakes, one must appreciate what inflation promises to explain. The universe, vast and structured as it is, arose from what appears to be practically nothing. On the largest scales, it exhibits remarkable uniformity in temperature, yet its matter is distributed unevenly /U 2014 galactic superclusters juxtaposed with immense voids. This contrast, the very fabric of the cosmos, poses a profound question: how did such complexity emerge? The answer may lie in the quantum realm. On the smallest scales, quantum particles behave unpredictably, their existence governed by Heisenberg's uncertainty principle. Virtual particle pairs spontaneously flicker into and out of existence without cause or effect. In the pre-inflationary universe, small enough to be dominated by such quantum effects, these fluctuations played a pivotal role. When inflation began, the rapid expansion stretched these tiny variations to macroscopic scales, seeding the large-scale structures we see today. From quantum noise, the architecture of the cosmos was born, feat so remarkable that Alan Guth famously called it the ultimate free lunch. The Antarctic scientists of 2013, armed with the BICEP 2 telescope, sought to verify this remarkable story. Their focus was on B-mode polarization, subtle patterns in the cosmic microwave background radiation that could only arise from the gravitational waves generated during inflation. When the team announced the detection of these B-modes in March of that year, the scientific world erupted with excitement. At last, it seemed, inflation had found its definitive proof. Yet science demands rigor, and as months passed, the initial confidence in the discovery waned. Cosmic dust in the polar sky, it turned out, could produce similar polarization patterns, casting doubt on whether the observed signals truly originated from inflation. The search for unequivocal evidence had hit a stumbling block, but the quest continued undeterred. Inflation's predictive power extends beyond the cosmic microwave background. Theoretical models suggest that it could generate primordial black holes, relics of the chaotic early universe formed less than a second after the Big Bang. These black holes, if discovered, would not only validate inflation but also offer insights into its mechanisms. Intriguingly, some theories propose that these primordial black holes might harbor entire baby universes. Isolated from our cosmos by the limits of their observable horizons, these universes would appear as singularities to us. Within them, however, their inhabitants would experience an expanding cosmos much like our own. Such a nested multiverse, hidden in the depths of black holes, challenges our understanding of existence and raises philosophical questions as profound as the scientific ones. At the heart of inflation lies the inflaton field, theorized to drive the rapid expansion of the early universe. Its existence is tied to a hypothetical particle, the inflaton, which remains elusive. This parallels the long search for the Higgs boson, which took nearly 50 years from its theoretical prediction to its discovery in 2012. The detection of the inflaton would mark a monumental leap forward in cosmology, connecting the quantum underpinnings of inflation to the large-scale structure of the universe. Despite the challenges, scientists remain optimistic. The tools of observation continue to evolve, and theoretical frameworks grow more robust. If inflation truly shaped the cosmos as we know it, its signatures are out there, waiting to be found. Whether in the faint polarization of ancient light, the discovery of primordial black holes, or the eventual detection of the inflaton, the proof of inflation grandeur lies just beyond the horizon. Inflation is both a triumph and a mystery. It elegantly explains the origins of the universe's vastness and structure, yet its mechanisms remain shrouded in uncertainty. For the Antarctic scientists braving the eternal night, the burden of proof is not a deterrent but a call to exploration. As they peer into the cosmos, they are driven by the same unyielding curiosity that inspired Guth's groundbreaking realization decades ago. In their work lies the hope that one day, the story of inflation will be fully written, not just as a theory but as an undeniable truth etched into the fabric of spacetime itself. Until then, the search continues, fueled by the belief that the universe, in its infinite complexity, will one day reveal its most profound secrets. In a lively bar near the University of Pennsylvania, Paul Steinhardt once raised a glass in celebration. His latest paper, Advancing the Burgeoning Theory of Inflation, had been accepted for publication. It was a moment of triumph, yet his mind was restless. Even as his peers discussed the promise of inflation, doubts began to creep in. The models he and his colleagues had painstakingly developed were mathematically sound, but their implications troubled him. For inflation to work, the parameters needed to be chosen with almost implausible precision. Without this fine-tuning, the model produced bizarre outcomes, chaotic multiverses of tangled, knotted space-time. Steinhardt unease grew with time, and today he has become one of inflation's most vocal critics. What was once his triumph has now become his target. Inflation was initially proposed as a solution to fundamental problems in cosmology. It explained how the early universe could have reached the observed levels of homogeneity and flatness without requiring an improbable degree of fine-tuning in its initial conditions. By positing an era of rapid exponential expansion just after the Big Bang, inflation smoothed out irregularities and flattened spacetime. For decades, it provided a coherent narrative for the cosmos' large-scale structure. Yet Steinhardt argues that inflation has introduced as many problems as it sought to solve. For one, the sheer variety of inflationary models has made the theory increasingly untestable. The parameters of inflation can be endlessly adjusted to fit almost any observation, rendering it, in Steinhardt words, pseudoscientific. A theory that cannot be falsified ceases to be a scientific theory at all. Moreover, inflation's success depends on the same kind of fine-tuning it was meant to avoid. Steinhardt analysis of the cosmic microwave background fine-scale structure revealed that only an infinitesimally small fraction of inflationary models could produce the universe we observe. The odds were so minuscule /U 2014 less than 1 in a googolplex /U 2014 that Steinhardt found himself questioning the entire framework. One of inflation's most contentious implications is the multiverse. In most inflationary scenarios, the process does not stop uniformly. Instead, different regions of space continue to inflate at different rates, creating a chaotic multiverse of bubble universes. While this idea is theoretically fascinating, it raises profound philosophical and scientific issues. If we exist in just one bubble, isolated from the others, how can we ever test the existence of these other universes? More troublingly, the chaotic nature of the multiverse challenges the idea of a coherent, comprehensible cosmos. Inflation was meant to provide simplicity, yet it seems to have spawned complexity on a scale that defies reason. For Steinhardt, the multiverse is not a feature but a flaw symptom of a theory stretched beyond its breaking point. Despite these criticisms, there is no clear replacement for inflation. Alternative models have been proposed, each offering intriguing possibilities but also grappling with their own limitations. Steinhardt himself has revisited the idea of a cyclical universe, Big Bounce, model in which the cosmos undergoes endless cycles of expansion and contraction. This approach, rooted in George Lima Phoenix universe, could resolve some of inflation problems, particularly the fine-tuning issue, if the entropy dilemma can be addressed. Other theories suggest that our universe birth was a ripple in a higher dimensional bulk of hyperspace, or that fundamental constants like the speed of light might have behaved differently under extreme conditions. These ideas, while captivating, are currently beyond the reach of experimental validation. The physics they invoke lie at the edges of our comprehension, tantalizing but elusive. For all its flaws, inflation remains the dominant paradigm in cosmology. Part of its appeal is its ability to be framed within the boundaries of known physics. Unlike some alternatives, which require entirely new frameworks, inflation can be described using the tools we already possess. This makes it a comfortable, if imperfect, solution for many scientists. Yet Steinhardt warns against complacency. He believes that the scientific community's reluctance to confront inflation shortcomings risks turning it into a dogma. To move forward, cosmologists must critically examine not only the theory itself but also their own assumptions and biases. The debate over inflation is far from settled. As observational techniques improve and theoretical models evolve, the next decade may bring clarity to these cosmic mysteries. Whether inflation is vindicated or replaced, the process of questioning and refining our understanding will drive progress. Paul Steinhardt dissent is a reminder that science thrives on skepticism. Theories, no matter how elegant or widely accepted, must withstand scrutiny. The cosmos may still hold secrets that defy our imagination, but the quest to unravel them is what defines our pursuit of knowledge. In the end, the history of the universe is not just a story of stars and galaxies but of human curiosity and the relentless search for truth. The dawn of a new age, the Trinity test, and the birth of modern physics. What lies within the smallest building blocks of the universe? Can the tiniest particles hold the power to reshape history and redefine the very fabric of civilization? These questions, once the domain of philosophers and speculative thinkers, gained terrifying clarity in the pre-dawn hours of July 16, 1945, when science unlocked one of nature's most devastating secrets. In the barren expanse of a New Mexico desert, the first light of dawn struggled to rise above the horizon. 30 minutes before sunrise, the stars had already surrendered to a shadowless blue hue suffusing the desert floor. The stillness was deceptive. This unassuming patch of ground had been meticulously prepared for a singular moment in history. Rising alone at the base of the Oscura Mountains, a 30-meter steel tower bore an ominous payload at its apex. Surrounding it, at precise intervals 9 kilometers away, 3 partially buried shelters housed a mix of soldiers and scientists awaiting the culmination of years of groundbreaking yet harrowing research. The air crackled with anticipation as a voice on the public address system began the countdown. Lying prone on the ground with their feet pointed toward the distant tower, the observers could not see the device itself. But they would soon witness its unimaginable power. At precisely 5:30 a.m., the quiet was shattered by an earth-shaking explosion. The steel tower evaporated, the desert floor melted into green glass, and the dim light of dawn was instantly overwhelmed by a searing brilliance that turned night into day. This was the Trinity test, the first full-scale detonation of a nuclear bomb. It marked the dawn of a new era in human history, one that would shape geopolitics, scientific discovery, and humanity's perception of its place in the universe. The events leading to Trinity began decades earlier, in a time when the atom was merely a theoretical curiosity. For centuries, philosophers and early scientists had debated whether matter could be infinitely divided or if there existed fundamental, indivisible units. By the early 20th century, experiments had revealed that atoms were not the ultimate building blocks of matter. Instead, they contained even smaller constituents, nuclei surrounded by electrons. The discovery of the nucleus opened the door to a new understanding of energy and matter. In 1938, German chemists Otto Hahn and Fritz Strassmann, along with physicists Lise Meitner and Otto Frisch, discovered nuclear fission, the splitting of an atomic nucleus into smaller fragments, accompanied by a staggering release of energy. This revelation coincided with the outbreak of World War II, and the implications of harnessing such power were immediately apparent. Albert Einstein, along with physicist Leo Szilard, penned a letter to President Franklin D. Roosevelt, warning that Nazi Germany might develop a powerful new weapon based on nuclear fission. This letter spurred the United States to initiate the Manhattan Project, an unprecedented effort to harness atomic energy for military purposes. The device tested at Trinity, nicknamed the Gadget, was a plutonium-based implosion bomb. Its design relied on carefully shaped explosives to compress a subcritical plutonium core into a supercritical state, triggering a chain reaction. This reaction released energy equivalent to 21,000 tons of TNT within a fraction of a second. The result was both a triumph of human ingenuity and a chilling demonstration of the destructive potential of nuclear science. The explosion not only vaporized the steel tower but also left a crater at the site, its floor transformed into a sheet of green, glassy material later named trinitite. Above the desert, a massive fireball ballooned upward, forming the now iconic mushroom cloud, a grim symbol of the nuclear age. If not for the exigencies of World War II, nuclear science might have taken a slower and more measured path. Before the war, the exploration of the atom was a niche pursuit, limited to small advancements and incremental discoveries. The pressures of wartime, however, accelerated this research, transforming atomic science into a cornerstone of modern physics. The success of the Trinity test marked a turning point, not only in military history but also in humanity's understanding of the universe. The same principles that unleashed the bomb's power inspired a deeper inquiry into the nature of matter and energy. The atom was no longer just a fundamental particle, it was a gateway to a hidden world of fields, forces, and particles, where the rules of classical physics gave way to the strange and counterintuitive laws of quantum mechanics. As the glow of Trinity faded, it left behind more than a mark on the desert floor, it ignited a scientific revolution. What are the true building blocks of the universe? How does energy shape matter at its most fundamental level? These questions propelled scientists deeper into the quantum realm and further back in time, seeking to unravel the mysteries of creation itself. The discovery of nuclear fission was just the beginning. The journey to understand matter led to the exploration of subatomic particles, the development of quantum field theory, and the realization that our universe operates on a tapestry woven from particles and waves, probabilities and uncertainties. This quest for understanding culminated in the discovery of the Higgs boson in 2012, a particle predicted decades earlier but only recently observed, a testament to humanity's relentless curiosity and determination. Trinity also raised profound philosophical questions. At its most fundamental level, what is reality? The principles of quantum mechanics suggest that particles exist in states of probability until observed, challenging our classical notions of objectivity and permanence. Is the universe we perceive a reflection of deeper, hidden truths? Or is it an emergent phenomenon, shaped by forces and dimensions beyond our comprehension? The legacy of the Trinity test is both inspiring and sobering. It marked the moment when humanity wielded the power to alter the fabric of reality, for better or worse. The knowledge it brought has driven advancements in energy, medicine, and material science, while also highlighting the ethical responsibilities that come with such power. The journey to understand the universe continues. From the splitting of the atom to the discovery of the Higgs boson, each breakthrough brings us closer to answering the age-old question, what is everything made of? And, perhaps more profoundly, what does it mean to truly understand the cosmos? As we continue to explore, we must remember the lessons of Trinity. The pursuit of knowledge is a double-edged sword, capable of both great good and unimaginable harm. It is up to us to wield it wisely, ensuring that the legacy of our discovery serves not just science, but humanity as a whole. Splitting the atom, a journey through science and philosophy. The origins of these inquiries date back to the ancient Indian philosophers of the 8th century BCE. They proposed a radical idea: nothing we perceive is truly real. Their extreme reductionist philosophy dismantled the world into its fundamental components. A cart, for instance, could be reduced to wheels, axles, and a yoke. Each of these, in turn, could be further dissected into smaller parts, until nothing remained but tiny, indistinguishable specks. What, then, are the objects of our experience? Are they merely assemblages of these specks, arranged to give the illusion of substance? This existential puzzle resurfaced centuries later among ancient Greek philosophers. Democritus and Leucippus, reflecting on the same problem, concluded that everything could be broken down repeatedly until an ultimate, indivisible unit was reached. They named these fundamental units atomos, meaning uncuttable. This profound concept laid the groundwork for a scientific journey that would span over 2 millennia. The transition from philosophical speculation to scientific inquiry began in earnest in the 19th century. John Dalton, an English chemist, synthesized ancient philosophies with contemporary scientific observations to formulate a groundbreaking theory. Dalton's work revolved around the analysis of chemical compounds. Each compound, he observed, behaved in unique and predictable ways. Methane, for example, consisted of carbon and hydrogen atoms, while nitrous oxide contained nitrogen and oxygen atoms. Dalton postulated that these compounds were constructed from indivisible building blocks, or atoms, specific to each element. Dalton's theory introduced the scientific concept of the atom, aligning with the ancient notion of atomos. Yet, as the 19th century unfolded, evidence began to challenge the idea of indivisibility. Atoms, it seemed, harbored secrets far more complex than Dalton or the ancients could have imagined. By the late 1800s, experiments probing the nature of electric charge unveiled a new kind of particle. J.J. Thomson, an English physicist, identified the electron in 1897, a negatively charged particle capable of moving independently of atoms. This discovery raised profound questions. If electrons were part of atomic matter, how could atoms remain indivisible? Ernest Rutherford provided a critical piece of the puzzle. In his famous gold foil experiment, Rutherford bombarded a thin sheet of gold with radioactive particles. To his astonishment, some particles rebounded, while others passed straight through. This led him to propose a revolutionary atomic model. Atoms consist of a dense, positively charged nucleus surrounded by orbiting electrons. Rutherford identified protons within the nucleus as carriers of positive charge, establishing the atom as a composite structure. While Rutherford's model explained much, it left one glaring inconsistency: the mass of certain atoms exceeded the combined mass of their protons and electrons. James Chadwick resolved this mystery in 1932 by discovering the neutron, a neutral particle residing within the nucleus. Chadwick's work earned him a Nobel Prize and deepened our understanding of atomic structure. With protons, neutrons, and electrons identified, the atom's indivisibility had been decisively disproven. The discovery of the neutron catalyzed a new era in atomic research. Scientists bombarded atomic nuclei with neutrons, altering their composition and occasionally splitting them. In 1938, Austrian physicist Lise Meitner, collaborating with Otto Hahn and Fritz Strassmann, identified this process as nuclear fission. A single neutron could split a uranium atom into smaller nuclei, releasing an immense amount of energy. Meitner's insights were groundbreaking. She named the phenomenon fission, drawing an analogy to cell division in biology. However, her pivotal contributions were overshadowed by sexism and anti-Semitism, leaving Hahn to receive sole recognition in the 1944 Nobel Prize. The practical implications of fission were profound and terrifying. Scientists quickly realized that a chain reaction of atomic splits could unleash unprecedented destructive power. This realization culminated in the development of the atomic bomb, marking a turning point in human history. The detonation over Hiroshima in 1945 underscored the dual-edged nature of scientific discovery, the potential for both immense progress and unparalleled destruction. With the atom split, the quest for fundamental particles intensified. Protons and neutrons, previously thought to be indivisible, were revealed to consist of smaller components called quarks. Electrons belonged to a different category of particles known as leptons. These discoveries expanded our understanding of matter's building blocks, but they also introduced new mysteries. Were quarks and leptons truly fundamental, or would further exploration uncover even smaller particles? The 20th century's advances in particle physics aimed to unify our understanding of matter. The Standard Model emerged as a framework, categorizing particles and describing their interactions. Yet, significant questions remained unanswered. For instance, what accounts for the vast majority of the universe's mass and energy? The discovery of dark matter and dark energy hinted at realms beyond the Standard Model, suggesting that the journey of exploration is far from over. As we probe deeper into the fabric of the cosmos, we find ourselves circling back to the questions posed by ancient philosophers. What is the nature of reality? Are the particles we observe the ultimate constituents of matter, or are they merely steps on an infinite ladder of discovery? Science and philosophy, once distinct domains, converge in their shared pursuit of these profound truths. The splitting of the atom represents both a triumph of human ingenuity and a cautionary tale. It highlights our capacity to unravel nature's deepest secrets and the responsibility that comes with such knowledge. As we stand on the shoulders of giants, from Democritus to Meitner, we are reminded of the boundless potential of human curiosity and the ethical imperative to wield our discoveries wisely. The story of the atom is far from complete. It is a testament to the enduring quest to understand our universe, a journey that continues to inspire, challenge, and transform humanity. Deeper we go, the story of quarks and the particle zoo. What lies beneath the surface of matter? Could there exist something smaller, something more fundamental than the atoms we once believed to be the indivisible building blocks of the universe? And if so, how deep does the rabbit hole go? These questions have driven the scientific imagination for decades, pushing the boundaries of our understanding of the cosmos and ourselves. This story begins not with laboratory experiments or sophisticated machinery, but with words. James Joyce, the renowned Irish writer, sought immortality through his literary creations. Yet, even in his wildest dreams, he could not have foreseen how his work, particularly Finnegan's Wake, would echo beyond the realm of literature and into the world of particle physics. Joyce's novel, famously dense and cryptic, captured the imagination of a young American physicist named Murray Gell-Mann, who would draw inspiration from its lines to name one of the most fundamental constituents of matter, the quark. By the mid-20th century, physicists had already cracked open the atom, revealing its subatomic constituents, protons, neutrons, and electrons. However, advances in technology soon uncovered a bewildering array of other particles, collectively referred to as the particle zoo. This term captured both the excitement and confusion of a field that suddenly seemed overrun with exotic inhabitants. Among these were hadrons, particles with mass, including protons and neutrons, as well as their more exotic cousins like pions and kaons. The proliferation of hadrons presented a puzzle. While each particle had its own unique properties, there were undeniable similarities between them. Why were they distinct yet fundamentally alike? This enigma echoed the earlier challenge of understanding the periodic table of elements, which had eventually been resolved by uncovering the atomic structure of matter. Physicists now sought a similar unifying explanation for the hadrons. In the 1960s, two physicists working independently arrived at a groundbreaking hypothesis. Murray Gell-Mann, based at the California Institute of Technology, and George Zweig, working at CERN in Switzerland, proposed that hadrons were not fundamental after all. Instead, they were composed of even smaller particles. Gell-Mann envisioned three subhadronic particles and whimsically named them quarks, borrowing the term from a line in Finnegan's Wake, 3 quarks for muster mark. Meanwhile, Zweig imagined for such components, which he called aces, drawing inspiration from the suits in a deck of cards. Both models provided a compelling framework for understanding the particle zoo. However, these ideas were purely theoretical until experimental evidence could confirm the existence of these subhadronic entities. The Stanford Linear Accelerator Center, established in the mid-1960s, became the proving ground for these bold hypotheses. At 3.2 kilometers long, SLAC's linear accelerator was the longest of its kind, capable of accelerating electrons to energies of 50 gigaelectron volts. By colliding these high-energy electrons with protons and neutrons, physicists could study the wreckage and glean insights into the subatomic structure of matter. In 1968, experiments at SLAC provided the breakthrough. The collisions revealed point-like particles within protons, consistent with Gell-Mann's theoretical quarks. These results confirmed that protons, like atoms before them, were not indivisible. Quarks were real, and they represented a new frontier in our understanding of matter. With the existence of quarks established, the next challenge was to determine their properties and varieties. Over the following decades, high-energy experiments and theoretical advancements identified 6 distinct types, or flavors, of quarks: up, down, strange, charm, top, and bottom. Each flavor possesses unique characteristics, including electric charge, mass, spin, and a property intriguingly named color. The term color in this context has nothing to do with visual hues but instead describes the way quarks interact via the strong nuclear force. This force, mediated by particles called gluons, binds quarks together to form hadrons. Quarks combine in triplets to create baryons, such as protons and neutrons, or in pairs to form mesons. These combinations follow strict rules dictated by quantum chromodynamics, QCD, the theory describing the behavior of quarks and gluons. Quarks are the foundation of all baryons and mesons, which in turn make up the nuclei of atoms. Protons, composed of 2 up quarks and 1 down quark, carry a positive charge. Neutrons, consisting of 2 down quarks and 1 up quark, are electrically neutral. Together, they form the nuclei of every element in the periodic table, giving rise to the diversity of matter in the universe. But quarks do not only form stable particles. In high-energy environments, such as those created in particle accelerators or cosmic events, quarks can also combine into exotic particles like lambda, sigma, and 11 baryons, as well as fleeting mesons. These particles often exist for mere fractions of a second, yet their study provides invaluable insights into the behavior of the strong nuclear force and the early moments of the universe. Quarks are not the only fundamental particles in the Standard Model of particle physics. Leptons represent another category of elementary particles, including the familiar electron as well as the heavier muon and tau particles. Each lepton also has an associated neutrino, a nearly massless and electrically neutral particle. Together, quarks and leptons form the building blocks of all known matter. Their interactions, governed by the fundamental forces of nature, underpin the structure and dynamics of the cosmos. Yet, the Standard Model, despite its success, leaves many questions unanswered. For all its elegance, the Standard Model does not explain everything. Why do particles have mass? The discovery of the Higgs boson in 2012 provided a partial answer, demonstrating how particles acquire mass through interactions with the Higgs field. Yet, the origins of the Higgs field itself remain a mystery. Moreover, the Standard Model cannot account for dark matter and dark energy, which together constitute approximately 95% of the universe's mass-energy content. Nor does it provide a unified framework for reconciling quantum mechanics with general relativity, the theory describing gravity. As we probe deeper into the nature of matter, we find ourselves revisiting the fundamental questions that have inspired humanity for centuries. Are quarks and leptons truly indivisible, or will future experiments uncover even smaller constituents? Is there a single, elegant theory that can unify all the forces of nature, from the strong nuclear force to gravity? The journey into the subatomic realm has already transformed our understanding of the universe. It has revealed a world of extraordinary complexity and beauty, governed by rules that challenge our intuition yet hold the key to understanding the cosmos. And as we stand on the brink of new discoveries, one thing is certain: the deeper we go, the more there is to learn. The mystery of matter, the hunt for the Higgs boson. What gives matter its substance? Why do particles have mass, and how did they acquire it in the first place? Without mass, electrons would not bind to protons, hydrogen atoms would not form, and the universe as we know it would be a lifeless void. These questions are not only fundamental to our understanding of physics, but also vital to comprehending the very fabric of the cosmos. February in Chicago is harsh. The wind, sharp and relentless, barrels through the streets, carrying the icy breath of Lake Michigan and depositing snow in corners of the bustling city. Yet, amidst the frigid air, the atmosphere inside the American Association for the Advancement of Science's 2009 annual meeting was anything but cold. Scientists gathered with anticipation, drawn to a singular lecture room where the hottest topic in particle physics was about to be discussed: the search for the Higgs boson, often dubbed the God particle. This was no ordinary scientific endeavor. It was a race, a contest of monumental stakes, pitting Fermilab's Tevatron in Illinois against CERN's Large Hadron Collider, LHC, straddling the French-Swiss border. The stakes were immense, as the Higgs boson was the missing piece of the Standard Model of particle physics, a framework describing the fundamental forces and particles shaping the universe. The LHC, a marvel of modern engineering, was purpose-built for this quest at a staggering cost of €3 billion. Yet, Just a month after its inauguration in 2008, disaster struck. A catastrophic explosion damaged several magnets in the accelerator, necessitating over a year of repairs. This unforeseen setback handed Fermilab a golden opportunity to take the lead. At the 2009 conference, Fermilab's scientists presented their progress, cautiously optimistic yet candid about the challenges they faced. The search for the Higgs boson was like hunting for a needle in a haystack, with the added complication that no one knew exactly what the needle looked like. The Higgs boson wasn't an arbitrary goal, it was the key to resolving one of the most perplexing mysteries in physics, the origin of mass. The Standard Model, developed over the latter half of the 20th century, provided an elegant explanation for the fundamental forces of nature. It described four forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each of these forces acted through specific particles known as gauge bosons. For instance, photons carried the electromagnetic force, while gluons mediated the strong nuclear force. W and Z bosons were responsible for the weak force, and a hypothesized graviton was theorized to explain gravity. Experiments confirmed the existence of most of these particles, cementing the Standard Model as a robust framework. However, one glaring issue remained: the question of mass. Quarks, the building blocks of protons and neutrons, had varying masses. The top quark, for example, was 75,000 times heavier than the up quark. Yet, the equations governing particle physics suggested that all particles should be massless. This contradiction was not merely a theoretical inconvenience, it had profound implications for the universe's evolution. Without mass, matter would never have coalesced into stars, galaxies, or life itself. The theoretical breakthrough came in 1964, when Peter Higgs and his contemporaries, Robert Brout and François Englert, proposed a radical solution. They suggested that in the early universe, particles emerged without mass. Soon after, a field, now known as the Higgs field, permeated the cosmos. Particles interacting with this field acquired mass, while others, such as photons, remained unaffected. The Higgs boson, a particle associated with this field, was theorized to exist as its physical manifestation. Finding this elusive particle became a central goal for physicists, for its discovery would confirm the mechanism that endowed the universe with mass. However, detecting the Higgs boson posed an enormous challenge. Its ephemeral nature meant it decayed almost instantly after being created in high-energy collisions, leaving behind a trail of particles that had to be meticulously analyzed. To generate the Higgs boson, scientists turned to particle accelerators, machines that collided particles at nearly the speed of light. The Tevatron, Fermilab's pride, was equipped to probe a specific energy range where the Higgs might appear. Meanwhile, the LHC, with its superior energy capacity and 27-kilometer circumference, was designed to search across a broader spectrum. After its repairs, the LHC resumed operations in 2010, marking the beginning of an intense period of experimentation. Protons collided within the massive detectors, generating unimaginable amounts of data. Analyzing this data required extraordinary computational power and collaboration among thousands of scientists worldwide. On July 4, 2012, CERN announced a momentous discovery. Two of the LHC's detectors, ATLAS and CMS, had independently detected a particle consistent with the Higgs boson. The data showed a clear signal at an energy of around 125 gigaelectronvolts, with a statistical confidence level high enough to declare it a discovery. Nearly 5 decades after it was first theorized, the Higgs boson had been found. Peter Higgs and François Englert received the Nobel Prize in Physics in 2013 for their contributions to this groundbreaking theory. The discovery not only completed the Standard Model but also marked a triumph of human ingenuity and perseverance. The Higgs boson now takes its place alongside the 60 other fundamental particles described by the Standard Model. These include the 6 flavors of quarks, 6 leptons, including the electron and neutrinos, and various gauge bosons. Together, they form the building blocks of matter and govern the interactions that shape the universe. However, the Standard Model, despite its success, is not the final word on the nature of reality. It cannot explain dark matter and dark energy, which make up 95% of the universe's mass energy content. Nor does it reconcile quantum mechanics with general relativity. Moreover, the graviton, the hypothetical particle of gravity, remains elusive. The discovery of the Higgs boson is not the end of the story but a new beginning. Scientists now seek to answer questions that the Standard Model cannot. What is the true nature of dark matter? Are there undiscovered particles or forces that extend beyond the current framework? And can we achieve a unified theory that connects all the forces of nature? To explore these mysteries, physicists are pushing the boundaries of technology and imagination. Plans are underway for more powerful accelerators, such as the proposed Future Circular Collider, which would dwarf the LHC in size and energy capacity. Meanwhile, experiments in astrophysics and cosmology aim to shed light on dark matter and the origins of the universe. The discovery of the Higgs boson is a testament to the power of human curiosity and collaboration. It demonstrates how theoretical ideas, born of abstract mathematics, can lead to tangible discoveries that reshape our understanding of the cosmos. The Higgs field, an invisible yet omnipresent entity, serves as a reminder that even the most fundamental aspects of reality are often hidden from view, awaiting discovery by those bold enough to seek them. As we continue to probe the mysteries of matter, we stand on the threshold of a new era in physics. The journey from the subatomic to the cosmic is far from over, and the quest to understand the universe's deepest secrets promises to inspire generations to come. The Dawn of Matter, a journey into the fabric of the universe. What is the true nature of reality? Is matter, as we perceive it, an immutable building block of the cosmos? Or does it conceal a deeper, more enigmatic truth? From the grandest galaxies to the tiniest particles, the universe challenges us to peel back layer after layer, revealing a complexity that defies comprehension. And yet, as we delve deeper, we find ourselves confronting not just the mystery of matter but the very nature of existence itself. Physicists, armed with precise calculations, estimate the number of fundamental particles in the observable universe. The number is staggering, more than 3 vigintillion quarks and electrons, a 3 followed by 80 zeros. These particles constitute the protons and neutrons in hydrogen and helium atoms, as well as their associated electrons. Even with such a mind-boggling count, when spread across the vastness of space, they average to just 1 quark-sized particle per cubic meter. The universe, it seems, is not so much full of matter as it is dominated by emptiness. Yet, for all the particles we can count and measure, they make up only a small fraction of the cosmos. Matter as we know it, the stuff of stars, planets, and living beings, constitutes a mere 5% of the universe. The remaining 95% is an enigma. 25% is thought to be dark matter, a mysterious substance that holds galaxies together, while 70% is attributed to dark energy, the force driving the accelerating expansion of the universe. Though these phenomena remain poorly understood, the matter we can observe tells a story that stretches back to the very dawn of time. Rewinding the cosmic clock to the very beginning, we arrive at a moment of unimaginable density and temperature. A trillionth of a second after the Big Bang, the universe was governed by a single, unified force. The distinct forces we recognize today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were melded into one. Particles, as we understand them, did not yet exist. Instead, there was perhaps a single type of boson, a progenitor of all the particles to come. As the universe expanded and cooled, this symmetry broke. The unified force split into the strong, weak, and electromagnetic forces. Gluons, photons, and W and Z bosons emerged as the carriers of these forces. Yet, at this stage, these particles were massless, and their behaviors were indistinct. It was only after a relative eternity, a trillionth of a second, that the cosmos cooled sufficiently for the Higgs field to emerge. The Higgs field permeated space, endowing certain particles with mass as they interacted with it. Quarks, leptons, and bosons acquired distinct properties, setting the stage for the formation of the universe as we know it. However, the temperature was still too high for quarks to combine into protons and neutrons. Instead, they existed in a turbulent, high-energy state known as a quark-gluon plasma, a primordial cosmic soup. Over time, as the universe continued to expand and cool, quarks began to bind together, forming composite particles like protons and neutrons. These nucleons clustered to form atomic nuclei, which eventually captured electrons to create neutral atoms. Hydrogen and helium emerged as the first elements, and from these building blocks, the universe began its transformation into a complex tapestry of stars, galaxies, and planets. While this story of cosmic evolution paints a picture of ever smaller building blocks nestled within one another, quantum mechanics reveals a more unsettling truth. At the smallest scales, particles such as quarks, leptons, and bosons defy classical understanding. They exist simultaneously as particles and waves, described not by precise locations but by probability distributions. This quantum uncertainty means that particles cannot be pinned down in space and time, challenging the very concept of their existence. Quantum field theory provides an even deeper insight. According to this framework, particles are not standalone entities but rather excitations in underlying fields. The universe is crisscrossed by at least 24 distinct quantum fields, each corresponding to a fundamental force or particle. These fields interact, creating interference patterns that give rise to the semi-stable particles we observe. A proton, for example, is not a solid object but a dynamic interplay of quark and gluon fields, shaped by the strong nuclear force. This perspective transforms our understanding of matter. The tangible objects we perceive are merely manifestations of underlying fields. The Higgs field, electromagnetic field, and others weave an intricate web through space and time, their ripples and interactions giving rise to the illusion of solidity. In this view, the universe is not composed of discrete particles but of continuous, interacting fields, with matter emerging as a transient, localized phenomenon. Even as we unravel the story of matter, vast mysteries persist. Dark matter and dark energy, which dominate the cosmos, remain beyond the grasp of our current theories. The standard model of particle physics, though remarkably successful, cannot account for these phenomena. Nor does it explain the nature of gravity at the quantum level, leaving room for new frameworks that may unify our understanding of the universe. Indian philosophers, nearly 3,000 years ago, speculated that the material world was an illusion. Modern physics, in its exploration of quantum fields and probabilities, echoes this ancient intuition. The universe, at its most fundamental level, may be less a collection of particles and more a symphony of interacting waves and fields, their transient peaks shaping the reality we experience. As we continue to probe the nature of matter, we are reminded that every discovery opens new questions. The journey into the fabric of the universe is far from over, and the mysteries that remain promise to inspire and challenge humanity for generations to come.